Well, here we are at chapter 4 in our summary. The topic here is congruence. It's one of the core topics of the entire year. We will discover here some theorems, some proof techniques that we will carry through us throughout all the year. And as we will find as well, that the primary object of our study in this chapter and throughout most of the rest of the year will be triangles. You now know that this is a proof class. It's been said many times, and you've seen a number of instances of proof, and we'll continue to do proof all throughout the year. But the specific topic of those proofs will be primarily about triangles. Now, not in every single case, but perhaps in 90% or more of the cases, ultimately our proofs will be about triangles. And this is the chapter in which that really begins. All right, so first of all, you need a definition of congruence. So let me build up to that. So let's say that we have a polygon, okay? And we know everything about that polygon, all its angle measures, all its side lengths. And imagine that we travel around the polygon, vertex to adjacent vertex, and it doesn't matter whether you go clockwise or counterclockwise. And as you go around, here's what you do. You construct a list of all angle measures and side measures that you find, like this. So here's a polygon, ABCD. You know how polygons are named. We do so by the vertices. We pick a vertex and we go around clockwise or counterclockwise and simply list all the vertices that we find. So here is one way to name it, polygon ABCD. And we've been given all the measures, both of angles and side lengths. And imagine that we pick a point, and as we go around, and a direction too, and as we go around, we list off all the measures that we find. So let us say that we start at vertex A, and then work our way around clockwise. If we do this, we'll have first a 62-degree measure, and then a side length of 2.2, and then a 98-degree measure, and so on. Now, imagine that you have a second polygon, and when you build the list for that second one, the two lists are the same. Okay, so in this case, I have the ABCD again, and I also have a second polygon, PQRST. And if you consider the angle measures and the side lengths, it will become clear that it is possible to build a list of consecutive side lengths and angle measures for the two that are identical. And that's what congruence is, okay? Congruence means that we can build two identical lists for a pair of polygons. Now, of course, it doesn't mean that, you know, whenever or whatever list you build for one and whatever list you build for the other, those will be identical. Because of course it's possible like to start at one place in one and another place in the other that don't correspond. But congruence means that it is possible that there is at least one way to build a list for the two polygons such that the lists are identical. Now, let's talk about this by means of the word correspond. So let us say that we have built two such lists and that they're identical to one another. Measures that are in the same position correspond. So first position corresponds, second position corresponds, and so on. And so here then is a compact way to give our definition of congruence. Two polygons are congruent if we can build lists for the two polygons such that angles and sides which correspond are equal. Here's another example for you, and I'll make a point with this example in just a moment. My question is this: are these two polygons equal? That is, can I build lists of consecutive side and angle measures for the two such that measures that are in the same position are equal? Well, yes. Let's say that I start at B in one and E at the other, and in the triangle on the left, I go around clockwise. So I'll go around clockwise. And in the second polygon, I will go around counterclockwise. And then consider the side lengths and angle measures as you find them. Okay, so angle B is equal to angle E, and then BC is equal to ED, and then angle C is equal to angle D, and then CA is equal to DE, and so on. And if you go all the way around, you will find that angles and sides that are in the same position are equal. So yes, these two polygons do correspond to one another. And the point that I wish to make here, it's another good example of congruence, but the point that I wish to make is that you don't necessarily have to go around in the same direction in the two polygons. Perhaps you have to go clockwise in one and counterclockwise in the other. You don't have to begin in like the same position in the two. Perhaps you begin on the left in one and the right in the other, and so on. You know, it's possible to like turn polygons, to flip them, and so on. So don't think that congruence means that you have to start in the same position and move in the same direction. It just means that it is possible to build two lists so that the lists are identical. All right, we have a symbol for congruence. It's what you see in front of you. It looks like the equal sign with a little squiggle on top. Don't confuse this with equality, which of course is just simply the two bars. Polygons are equal only to themselves because in general, the only object to which an object is equal is itself. But of course, distinct polygons can be congruent, like the example that I gave you just a moment ago. I'll go back. ABC is congruent to EDF, and those are distinct polygons. All right, now congruent statements. A congruent statement is where you say that one polygon is congruent to another. They all have a particular form. It begins with the name of one polygon, followed by the congruent symbol, and then third is the name of the second polygon. And what you must understand about congruent statements is that order matters. The names of vertices that correspond have to come in the same position. So here are the two quadrilaterals again, ABCD and PQRS. Here are valid congruent statements. ABCD congruent to PQRS. That's the first of the ones that I gave you. And the reason that that is a valid congruent statement is it gets the congruences right. A does correspond to P. You see them both in first position. B does correspond to Q. C does correspond to R. D does correspond to S. And how do we know that those correspondences are correct? Well, look at what's there in the two polygons. At A is an angle of 62 degrees. Well, at P is an angle of 62. Look at what's at B. B is an angle of 98. Q is also an angle of 98. So that gets the congruences right. Now, any congruent statement that sets up those same correspondences is also valid. So it's also perfectly correct to say that CDAB is congruent to PQRS. Notice that this makes C and R correspond because they're both in first position, but the first congruent statement did as well. C and R were both in third position, so and both they correspond. B is in second position, Q is in second position, so they correspond, which is also true in the first congruent statement. So those two congruent statements set up the same correspondences, so they're both perfectly valid. In fact, they make the same claims. We won't even really distinguish them. They both say correctly that the first polygon is second to the congruent, to the second. Okay, now of course there will be invalid congruent statements. We could not say, for instance, that ABCD is congruent to PSRQ, and why not? Well, A does correspond to P, both in first position, but B does not correspond to S. At B, we find a 98-degree angle. At S, we find a 136-degree angle, so they don't correspond, so they should not occur in the same position. And of course, there will be other invalid congruent statements as well. Okay, so let's write a valid congruent statement for the polygons that you see in front of you. We often use the triangle symbol to indicate that we have a triangle. We don't have to in this context, but I often do. So let us call the first CBA. Now, as for how you name the first polygon in a polygon congruent statement, well, that's ultimately up to you, just so long as it's a correct polygon name. But once you have chosen an order of letters for the first polygon, then the order of letters in the second is not a choice that you can make. Okay, so to what does C correspond? Well, C obviously corresponds to D, and then in the first triangle we went to B, and to what does B correspond? Well, B corresponds to E, and then we ended up at A, and to what does A correspond? That is, it is F. So if we call the first CBA in this congruent statement, we must call the second DEF. Now, let us say that we know somehow or another that two polygons are congruent. Perhaps we're given that, perhaps that's a statement that we reach in the course of a proof. We may then immediately conclude after that sides and angles which correspond are equal in measure. Of course, just by the definition of polygon congruence. And this is a very common move that we will make in our proofs. It's so common that it would be good to have an abbreviation for this, and we do. It's CPCPE, which is short for corresponding parts of congruent polygons are equal. And that's really just a short statement of the definition of polygon congruence. Now, very often in the case of triangles, we will use CPCTE instead. Notice the T. And that, of course, stands for corresponding parts of congruent triangles are equal. Now, if I were you, I would pause for just a moment here and say that to myself a number of times, just to make sure you know what this abbreviation stands for. It will be used very often. All right, so let's say we know that, let's see, that's a pentagon, isn't it? A five-sided polygon, that ABCDE is congruent to ZYXWV. We know how congruent statements work, so we should be able to answer these questions. The measure of angle A is equal to the measure of angle Z. Why? Because they're both in first position. the measure of angle W is equal to the measure of angle D. Why? They're both at next to last position. The length of segment CD, there it is, CD, has to equal the length of segment, well, XW. Why? CD is third position and then fourth, and XW is also third position and then fourth. And then finally VZ, which is last and then first from the second polygon, would have to equal EA, or if you like, of course, AE, because those are the same. Now, just a quick reminder, we saw this a moment ago. If we know that two triangles are congruent, that's really 6 equations, right? It says that every angle of one is equal to an angle of the other. That's 3 angle equations. It says that every side of one is equal to a side of the other. That's 3 side equations for a total of 6 equations, 6 pieces of information. However, and now the chapter starts to get really good. We will find that we can prove triangles congruent with less than 6 pieces of information. Indeed, we will find that 3 will do if they're the right 3. And these are shortcuts to congruence. You don't need, in certain situations, 6 equations before you can say that 2 triangles are congruent. Indeed, in some situations, all you need is 3. And the first of these shortcuts to triangle congruence is the so-called SAS, triangle congruence postulate. And the SAS stands for side angle side. And what it says is this: if 2 sides and the included angle of one triangle equal 2 sides and the included angle of a second triangle, then those triangles are congruent. And note that by included angle, we mean the angle in between. Okay. Now, of course, you would like to have a picture for this, and here it is. So I have, once again, 2 triangles, a triangle ABC and a triangle RST. Notice that I have 2 sides of ABC equal to 2 sides of RST. In particular, AB is equal to RS and BC is equal to ST. And notice as well that we have the included angles equal. In triangle ABC, the included angle, that is the angle in between, is angle B. And in triangle RST, the included angle is angle S. So I have 2 angles and, 2 sides in the included angle of ABC equal to 2 sides in the included angle of RST. And it follows that the 2 triangles are congruent to one another. And this, as I mentioned a moment ago, is a postulate. This is one of our basic assumptions. Okay, now what follows? Once we have used SAS congruence to conclude that a pair of triangles are congruent, well, at that point, we can invoke CPCTE and say that all the other pairs of sides and angles that correspond are equal as well. So if you look at the 2 triangles below, ABC and RST, we can say first that they are congruent by SAS, and then it follows by CPCTE that angle A is equal to angle R, also that angle C is equal to angle T, and finally that side AC has the same length as side RT. This all follows by CPCTE once we have said the triangles are congruent. Now, let's put together some SAS congruence proofs. That is, we will apply SAS congruence to draw conclusions about triangles. So how do these go? Prove, first step, prove if necessary, and sometimes it's all in the given, and so it's not necessary, but it often is. Prove that 2 sides in the included angle of one triangle equal 2 sides in the included angle of a second triangle. Once that has been done, we may say by SAS that the triangles are congruent, and then, if necessary, depends on the proof, if necessary, we may infer by CPCTE that any pair of sides or angles which correspond are equal to one another. Okay, so let's actually do an example here. So we have a diagram, as you see. We have a given. The given says that AM is equal to CM, and here's a suggestion. If the given hasn't been labeled into the diagram, take a moment to do that. So I labeled that AM is equal to CM. I labeled that BM is equal to DM, and I wish to prove that triangle AMB is congruent to triangle CMD. Okay, so statement from by. Later on, we'll start to give proofs in a different style, so-called paragraph style, but for now, we'll continue to give column type proofs. Those are the ones that you have seen. Okay, so let's see. What do we have and what do we need? Well, we have 2 sides of triangle AMB equal to 2 sides of triangle CMD, so that's 2/3 of the way to application of SAS congruence. What we also need is that the included angles are equal as well. So here are the included angles. Angle AMB in one, angle CMD in the other. And the question is this, well, are they equal? And if so, how do we know that they are equal? Well, you should recognize by now that those are actually vertical angles. And we have proven in the previous chapter that vertical angles are equal to one another. So we can immediately say that the measure of angle AMB is equal to the measure of angle CMD. And that follows from the given as pictured in the diagram by the vertical angles theorem, by VAT, which of course we abbreviate. And then, and at this point, we now have two sides of the included angle of one triangle equal to two sides of the included angle of the second triangle. So we may say that triangle AMB is congruent to triangle CMD, and that follows from the given, which gives us equality of sides, and also line number 2, which gives us the equality of included angles, by SAS congruence. And we'll also add the congruence to SAS because in a later chapter we'll find that there's something called SAS similarity. We want to make sure that we don't confuse the two, so call that SAS congruence. All right, here's another. So we're told that BM, so look at the diagram, segment BM bisects angle ABC. Okay, so we know what that will mean. That will mean that we create a pair of equal angles, and we know as well that AB is equal to BC, and we wish to prove that the triangles are congruent. That is, triangle ABM is congruent to triangle CBM, and then it will follow by CPCTE that the measure of A is equal to the measure of angle C. Okay. Now, how will we actually prove that triangle ABM is congruent to triangle CBM? Well, we have a pair of equal sides, we have a pair of equal angles. We also need another pair of equal sides, but notice that we get that as it were automatically because we don't even have a pair of equal sides, rather we have a side in common. Now the question will of course arise about how it is that we will actually say this in the proof. The way that we will say it is that BM is equal to BM, and read that as BM as it appears in one triangle is equal to BM as it appears in the second triangle. And we have a property, as I hope you remember, that allows us to write that BM is equal to BM, and that's called reflexivity. Okay, so here we go, statement from by. Now, we have the given, of course, which as always, I don't take the time to write out again. Okay, so first of all, we need to say that the measure of angle ABM is equal to the measure of angle CBM. And we know that's true by the definition of bisector. By definition, a bisector creates a pair of equal sub-angles. And so we've now said that they're equal to one another. Let us also say that BM is equal to BM. That's the shared side. That's the side that appears twice over, as it were. And of course, it's equal to itself. That also follows from the given, as pictured in the diagram, by, I'll just simply call this reflexivity. And then at this point, glance back up at the diagram, we have two sides in the included angle of triangle ABM equal, respectively, to two sides in the included angle of triangle CBM. So we can now say that triangle ABM is congruent to triangle CBM. And that follows from, well, let's see, we need the given because the given contains AB is equal to BC. We need line number 2 because that includes an angle equal to an angle. And also we need line number 3, which gives us a second pair of equal sides. So the triangles are congruent from all of 1 and 2 and 3 by SAS congruence. And then, once we know the triangles are congruent, we may conclude that another pair of sides or angles that correspond are equal to one another. So we can conclude that the measure of A is equal to the measure of C. And notice that that really does follow. Look back at the triangle congruence statement on line number 4. Notice that on the left, A occurs first. Notice that on the right, C occurs first. So they do correspond. So we may then conclude that the measure of A is equal to the measure of C by CPCTE. And this is one of the most common moves that we make in our proofs throughout the entire year. Typically, not always, but typically, when we wish to prove that a pair of angles or a pair of sides are equal, the way that we do this is that we first prove that triangles are congruent, and then we use CPCTE to conclude that a pair of sides or angles are equal to one another. And that's really ultimately the kind of work that triangle congruence does from us. It allows to go from the equality of certain sides and angles to the equality of other sides and angles. And the way that it allows us to do this is that we first conclude that triangles are congruent, and then we use CPCTE. Okay, so now let's talk about isosceles triangles. The conclusion that we draw about them, the theorem that we prove, will ultimately come to us from SAS. Okay, so first of all, the definition. An isosceles triangle has at least two sides of equal length. Do focus on that at least two. One way to have at least two, of course, is to have two. Another way to have at least two is to have three. Okay, and we'll come back and talk about that in just a moment. Now, first of all, a little bit of anatomy. We have language that we use to describe the parts of isosceles triangles. So the pair of equal sides we call legs. The base is the third side. The base angles lie opposite the legs. And here's what I mean by that. So the legs in this case are obviously AB and AC, the equal sides. Opposite in the triangle to leg AB is angle C, and opposite leg AC is angle B. Okay, and then finally, by the vertex, we simply mean the point of intersection of the legs. Now, I know we use vertex generally to refer to points of intersections of sides of a polygon, but in the case of isosceles triangles, when you talk about the vertex, you mean a special vertex. You mean the vertex that is the point of intersection of the legs. Now, let me come back to that definition of isosceles again, the part that says at least two. Well, do be clear here that on our definition of equilateral triangles are isosceles. And why? Well, an isosceles triangle has at least two sides equal. And if you have all three sides equal, well, then, of course, you have at least two. And moreover, we can choose any two sides and call them the legs, because the legs are simply a pair of equal sides, and since all sides are equal, there's more than one way to choose a pair of equal sides. So the legs could be AB and BC, the legs could be AB and AC, or the legs could be BC and AC. That is, any way to choose two sides, those could be the legs. Okay, now to the isosceles triangle theorem, which is one of the most important theorems of the year. It gets used all throughout the class. It has an abbreviation, of course, right? All the important theorems have abbreviations. We simply call it the ITT. And it says this: in an isosceles triangle, the angles opposite the equal sides are themselves equal. So look at the diagram. We have isosceles triangle ABC. The legs, as marked, are AB and AC. We may prove, that is, we may conclude, that the angles opposite those equal sides are themselves equal. So angle B opposite side AC, angle C opposite side AB, we may conclude that those are equal. So how do we prove this? Well, we have to make a new move in the proof, a kind of move that we haven't seen so far. We're set up to make this move, but we actually haven't done it yet, so we have to pause for a moment. What we need to do is we need to make an addition to the diagram. And when we do that, when we add something into the diagram, we say construct, okay? Well, what may we construct? I've got a handout for that. It's the constructions handout. If you go to my website, thinklogical.net, and look for the link that says definitions, postulates, theorems, constructions, and then click on constructions, you'll see the list of all allowed constructions. And in this context, that is the proof of the ITT, we need one particular construction, which there is called construction 5, C5. It's the angle bisector construction. And what it tells us is this, is that if we have an angle that is given an angle, we may construct a ray through its interior that creates a pair of subangles of equal measure. That is, we may construct an angle bisector. And as for the justification of this, how do we know that we may construct an angle bisector? Well, it's really just an immediate consequence, as I mentioned a few chapters ago, an immediate consequence of the protractor postulate, because the protractor postulate says that we can add rays into our diagrams and thereby create angles of whatever measure we please. And in this case, of course, we would simply create two subangles that have exactly half the measure of the original angle. Okay, so then here's what we do as the first step of the proof. We take our isosceles triangle ABC and we construct the bisector, you see it there, AD, of angle BAC. Okay, So that is our construction. And then with that, I suspect you know what we need to do. And as a matter of fact, I'll simply refer you back to a proof that we gave earlier. That is the proof in which we proved that we had a pair of congruent triangles. In this case, those would be BAD and CAD. We'll, of course, use the definition of bisector to get that the measure of angle BAD is equal to the measure of CAD. Then we'll use reflexivity to say that AD is equal to AD, and then it will follow by SAS congruence that BAD is congruent to CAD, and then it will follow that the measure of B is equal to the measure of C by CPCTE. So it's very much like that previous proof that we gave, once the angle bisector has been constructed into the diagram. All right, so on to another triangle congruence shortcut. This is SSS congruence. Okay, before we had SAS congruence. Here now we have SSS congruence, which stands for side-side-side congruence, and what it says is this: if the sides of one triangle equal the sides of a second, then those triangles are congruent. Like in the diagram that you see, we have two triangles, ABC and RST. Each side of ABC is equal to a unique side of RST. That is, all the sides of ABC and RST are equal, as marked, and it will follow then by SSS congruence that the two triangles are congruent. And what will this do for us? Well, typically what we'll do, not always, but typically, what we'll do is we'll use SSS to prove that a pair of triangles are congruent. Of course, that is possible. And then we will use CPCTE to conclude that angles which correspond are equal as well. So really what we're able to do here is this. If we begin with triangles that have their sides equal, we may then conclude that their angles are equal as well. That is, triangles with equal sides also have equal angles. And the way we get there is that we first apply SSS congruence to say that the triangles are congruent, and then we apply CPCTE to say that angles which correspond are equal as well. All right, so here's an example of an application proof, a very simple one. Okay, so look at the diagram. And remember, I should mention this again, that in our diagrams, whatever looks straight is straight. That's not something that I explicitly state. I allow the diagram instead to talk for itself, to speak for itself. So we assume then that the path from A to C to E is straight because it does look that way. And what we're given then is that AB is equal to ED as marked. We're given that BC is equal to DC as marked. And then we're also given that C is the midpoint of AE. And we wish to prove that triangle ABC is congruent to triangle EDC. And how will we do that? Well, think about what midpoint means, okay? Midpoint means by definition that we create a pair of equal segments. So it will follow that AC is equal to CE. And then once we know that, we may conclude that triangles are congruent. So it's really a very short proof. So statement from by. Line number 1 is the given. And then in line number 2, we say that AC is equal to CE, and that follows from the given, that is line number 1, by the definition of midpoint. And then at this point, we know that all three sides of one are equal to the three sides of the other. So it follows now that triangle ABC is congruent to triangle EDC. And that follows from, well, we need the two side equalities in the given. We also need the equality in line number 2. And it follows by SSS congruence that the triangles are congruent. So there's a very simple proof for you. Here's another that we wish to do. So we have a quadrilateral ABCD. And we are told that in this quadrilateral, AB is equal to AD as marked. We are told that BC is equal to DC also as marked. And we wish to prove that the measure of angle ABC is equal to the measure of angle ADC. Well, how do we do this? Remember the tip that I gave you earlier. Typically, when we wish to prove that a pair of angles are equal, we first prove that triangles are congruent, and then we use CPCTE to prove that the angles that correspond are equal as well. Okay, now we have an obvious problem here, right? How will we possibly prove that triangles are congruent when we don't even have any triangles in the diagram to begin? Well, what we need is another construction, okay? If you look at that constructions handout, you will find that if we are given a pair of points, we can construct the line through them. We can construct a ray from 1 through the other. We may also construct the segment that goes from one to the other. So, oops, sorry. That happens when my hand touches the screen in an unexpected way. So by C1, we may construct segment AC. Okay, so we will construct segment AC. So there we go. And then at this point, we're going to launch into the proof. Now, the way I will treat this construction is I will treat it as it were, an addition to the given. We just extended the given. Okay, so statement from by, and typically what we'll do with constructions is that before we launch into the column proof, we will simply write out the constructions that we added to the diagram. Okay, so that's now given. That's now part of the given. So line number 1 is the given. And then, well, we need to prove that our triangles are congruent to one another. We're almost there. We have two sides of one equal to two sides of the other. That is, two sides of ABC are congruent to two sides of ADC. We'll need to note, of course, that side AC is common to them. That is, it is a shared side, and we'll do that with reflexivity. And then we may say that triangles are congruent. Okay, so we will note that AC as found in one triangle is equal to AC as found in the other. This is based on the given. Okay, that is at least the given as supplemented by the construction. Okay, and that follows by reflexivity. How about just REFL for reflexivity? And then at this point, I have three sides of ABC equal to three sides of ADC. And it follows then that they are congruent to one another. So triangle ABC is congruent to triangle ADC. And that follows from, well, we need the equalities in the given. We also need the equality on line number 2. And the reason, of course, is SSS congruence. And then once we know the triangles are congruent, we may say that angles that correspond are equal. So it follows that the measure of angle ABC is equal to the measure of angle ADC. And that follows from the congruence found on line number 4 by CPCTE. So there it is again. How did we get this pair of angles equal? Well, we made triangles, we proved the triangles congruent, and then we used CPCTE to draw the conclusion that we wanted. That's just such a common move in our proofs in this class. All right, so in this chapter, we will have 3 total shortcuts to triangle congruence. In the next chapter, we'll have another as well. The third one in this chapter is so-called ASA congruence, which I'm sure you could guess stands for angle side angle congruence. And it says this: if two angles in the included side, that is the side in between, of one triangle equal two angles in the included side of a second triangle, then those triangles are congruent. And here's a picture to illustrate this. Okay, so I've got two triangles, ABC and RST. I have angle A in one equal to angle R in the other. I have angle C in one equal to angle T in the other. So I have two pairs of equal angles. And then the included sides are equal as well. That is, the sides that are in between the equal angles are also equal. Okay, so I have what I need for ASA congruence. So I may say by ASA that ABC is congruent to RST. And let's do an application proof. Okay, so let's assess the situation here. So I've got a figure very much like what I had before. I've got two triangles that share the side AC. And we're told that AC bisects both angle BAD and angle BCD. Well, because it bisects angle BAD, we'll get a pair of equal subangles. And because it bisects angle BCD, we'll get a second pair of equal subangles. And now consider triangles ABC and ADC. That is the top and the bottom. I have two angles of one equal to two angles of the other. And notice that I also have a side in common, that is side AC. And for both triangles, that is the side included between the equal angles. So it will follow by ASA congruence that ABC is congruent to ADC. And then we can use CPCTE to conclude that AB is equal to AD. Okay, so here we go. Statement. And notice in this case, we didn't have to add a construction, so that's not a step in the proof. So as always, we have the given. And then we will say, I tell you what, I'm going to label some angles just to make my life easy. You're always free to do this, okay? But of course, if you introduce names into a diagram, you need to show me what you've done, because otherwise I won't know what you mean. So just simply draw them into the diagram. So I know that the measure of angle 1 is equal to the measure of angle 2. And likewise, for the same reason, so I'll put it on the same line, the measure of angle 3 is equal to the measure of angle 4. This follows from the given just by the definition of bisector, or definition of bisects. That's what bisectors do. And that we also know that in our two triangles, AC is a shared side. That follows from the given, because the whole setup that you see in the diagram is just the given. So that follows from line number 1 by reflexivity, REFL. And now it follows that triangle AB, oops, let me remove that. It follows that triangle ABC is congruent to triangle ADC. And let's see, what did we need to get there? Well, we needed the angle equalities on line number 2. We needed the side equality on line number 3. So there they are, 2 and 3. And then this follows by ASA congruence. And then once we know the triangles are congruent, however we happen to know that, in this case we used ASA, we may then say that any pair of side or angles which correspond are equal. And here's a pair of sides that correspond AB and AD. Notice that if you look at the congruence statement on line number 4, AB is first, second on the left, and AD is first, second on the right, so that really corresponds. So it follows from 4 that AB is equal to AD by CPCTE. And with that, we are done with the lesson about congruence. The next chapter will be about parallels. And with that, we have some of the most important tools that we use in this chapter. That is congruence and then parallels. All right, talk to you later.